Welcome all to this lectures. I am Manoranjan Oja, Assistant Professor, Department of Basic Science Chemistry, ASR University. Today our topic is dielectric properties of the materials. So we'll discuss what is the dielectric property and what the materials having these properties has the applications. Two things we'll discuss here. So what is dielectric materials? So dielectric materials is a electrical insulator that can be polarized when subject to a external electric field. Means that we have a different of compound that is called conductor, semiconductor, or insulator. But dielectric substance is belongs to the conduct insulator properties. That means there is a huge energy difference or band gap between the between the valence band and conduction band. It is more than 3.0 electron volt. So this is called a insulator. So this insulator compound, when we are using in the subject to we are applying or it is placed in the subject of external electric field, then the materials act in a different way. So those materials we call the dielectric materials. So in this material, there is as the conduction band and valence band energy difference is very large or band gap is very large. So it does not flow the electron from the valence band to conduction band. This transformations or the transitions of the electron cannot take place easily as in the conductor or semiconductor. So this flow of electrons, normal or free flow of the electrons or electric charge is not possible in these compounds. So what happened when we placed this kind of a compound in the presence of external electric field, then the charges or the electrons inside the molecules or compound, they will oriented in a specific way, so there will be some polarizations in the compound. So that is the dielectric materials. So the materials does not have a free flow of the electrons or the charges, but when we place in the external magnetic field, the localized charge or the electrons, they will orient themselves in a different way so that there will be localized charge and the compound will be polarized compound. So this is called the dielectric substance. So that's that polarization is happening due to the external electric field. So for this one, this compound can be useful in different purpose like capacitors or transformer or microwave device, insulating cables, sensors, or electronic components. That's why it is very important to understand what are the properties of the dielectric materials and how it behaves and where we can use these materials. So in one way, the dielectric properties of the material describes that how a material interact with an electric field and how much the energy it can store or dissipate. Dissipate means it loss or it is passing out or it is going out. That is called dissipate, or how much energy it can store. So means two things it is here, that the materials is interacting with the electric field. Then after the interactions, then we are now going to calculate or understand the how much electric charge it can store or dissipate from this material. These properties depends on internal structures of the materials, frequency of the applied electric field, temperatures, and material compositions. So we can categorize these properties of the dielectric substance. One is that what is that materials, that which materials we are going to use it, what is the internal structures of the materials, means inside the compound how the ion will be arranged. We are going to organized or oriented when electrical field will be applied. So means one is the structures of the materials, second is that the frequency of the applied electrical field, and other conditions, the temperature or material compositions. So electric polarizations, what we are talking about, that electric polarization is that inside the materials there will be different kind of charges, positive charge or negative charges there will be. So when it will be placed in the electric field, then due to this electric field, these positive charges or negative charges in the materials, they will displace slightly in opposite directions. So then we'll get a polarization is the molecule, or it will create the dipoles, then polarizations of the molecule it will be created. So that is called the electric polarization, because we have applied the electric field. For example, let's say for a compound plus charge, this orientation is this directions, and minus charge, this orientation is exactly in the 180 directions, then total polarization is zero. So this is with dipole we are getting, it is completely zero. But let's say one positive directions in this way, and then negative polarization, let's say negative polarization in this way. So then there will be a dipole, net dipole in one particular directions. For dielectric substance, we have this kind of a one dipole moment in the molecule due to the displacement of positive charges and negative charges. So, and they are not exactly opposite to each other. So that's what we are getting, a net dipole moment of the molecule. So if net dipole moment of the molecule is created due to the electric field, then we say that is has a polarization is there in the molecules, and that can be calculated. This total dipole moment divided by volume, means total number of the what is the volume of the materials where we are calculating the total dipole moment, we are dividing by this volume. So P, that is called polarizations, the electrical polarizations, equals to total dipole moment divided by volume. So the polarization reduces the effective electric field inside the dielectric or influencing its electrical behavior. So what happened, that electric field when we are applying, due to the polarization, dipole moment is there, so it will reduce the electric field it will experience, or outside whatever that we applied the electric field, it will reduce that one in the inside the dielectric substance. So what are the types of the dielectric substances? Types of the polarizations can happen in the molecules or compounds. We'll discuss here. Different polarization mechanisms operate in dielectric materials depending on the nature of the atom or molecules and the frequency of the applied field. So two things is there. One is the about the materials, which materials we are going to use it, and what is the arrangement of the materials or the structures of the materials, and how the inside the molecule compounds, the atoms or molecules are arranged. This is one property that is related to material properties. Second thing, outside we are going to use the applied field. So that applied field, how frequency, what is the frequency we are using for that applied field. So two ways these polarizations can be varied. So one is the which materials we are choosing, and second is the what is the frequency of the applied field we are applying. For example, let's say electronic polarization. Electronic polarization is that it occurs for all dielectric substance, means in any dielectric substance if you take, these electronic polarizations can be seen. So what is happening, that applied electric field displaces the electron cloud relative to the nucleus. So it is actually when we are applying the electric field, it displays the electron cloud. Means for let's say in an atom, that molecule nucleus will be there, and surrounding of it, in different energy level, electrons will be there. So it when it will apply the electric field, then this electron cloud in the every energy level, that will be displaced from this part. So then one side little bit will be because of the displacement, this there will be net dipole moment in the molecules. So for that one we can get the polarization, and this is called electronic polarizations, because the electron cloud is displaced due to the electrical field. So this is called electronic polarizations. This is predominantly observed in high frequency, means whatever the applied field we are applying here, so that will be when it will be applied in higher frequency, then we can observe this kind of a property. And it is present in non-polar and polar materials, both cases, which is having the permanent dipole moment, that is polar molecules, and does not have the permanent dipole moment, it's called non-polar molecules. Both cases we can be seen this kind of a polarizations. Then it is called ionic polarizations. This occurs in the ionic solids. For example, NaCl here, where Na plus and Cl minus ion is there. This positive ion Na plus and the Cl minus, there will be one arrangement of these molecules, and total molecule is neutral. Now, when we applied the electrical field, then the positions this of the Na plus and Cl minus will shift, and their directions will be little bit in different directions. So if their direction is changed, then the overall the dipole moment of the molecule will be created. So no longer it acts as a non-polar, it will be dipole moment of compound will be there due to the applications of the electrical field. So when this ion movement due to the ion shifts, when the dipole moment is created and polarization is happening, so we call it the ionic polarization, because in ionic compound, due to the ion movement or shifting in opposite directions, so we are getting the polarizations. So this is called ionic polarizations. So it normally had happened the low to intermediate frequency, means whatever the electric field we are applying here, and that in low to intermediate frequencies, this kind of ionic polarizations happen inside the molecule. Another one is orientation dipolar polarizations. So it is occurs in the polar molecules. So we'll discuss here polar molecules means, let's say for HCl. In this HCl molecule, the electronegativity of the Cl is much more higher than that of hydrogen. So in the bond there is two electron. It is one is given by the Cl atom, another from the H atom. So due to the electronegativity differences, the electron cloud it moves towards the more negative atom. So then the electron cloud or two electron is no longer at the middle of the this bond, but slightly shifted to the more to the electronegative atom. So then for that shifting of the electron cloud, so there will be a little bit delta plus charge in the low electronegative atom side and delta minus charge in the high electronegative sides. So when these properties is created, we call this compound its acts as a dipole. So now little bit delta plus or delta minus is there. So charge separations is there. That is very minute. That's when it is created, then we will get a permanent dipole of the molecule. That is called polar compound. For example, for CO2, there is a dipole moment change from this one delta minus, and this is delta plus for this one, and for this one delta minus, and for this one also delta plus. So overall this side it is this direction dipole and this is dipole. Then overall if you see the opposite directions, so net dipole equals to 0. But here there is some dipole is there. So this is called polar compound. This is non-polar compound. So dipoles align themselves in the directions of the applied electric field. So when a compound is having the dipole, then dipole can be oriented in the directions of the applied field. When you are applying the electric field, this can be oriented in the directions of the applied electric field. So then we'll get this called orientations polarizations. Orientations means this dipole is there or dipolar in compound, and they will orient in the directions towards the applied electric field. Then whatever the polarizations we got, we call orientation polarization or dipolar polarizations. It is strongly temperature dependent and effective at low frequencies. So when the temperatures will be different or it will be increased, so this directions of the dipole can change. So that's why it is dependent on temperature strongly. Another is called space charge polarizations. So occurs due to the accumulations of the charge at interface or grain boundaries or defects inside the molecules. If there some defects will be there in, and also for grain boundaries. Grain boundaries means in the crystal structures, the orientations of the crystallite in the compound will be in different way, in different directions, and when these two different crystallite come to meet together, then this boundary we called, that is called grain boundaries. And in that, this accumulation of the charge in that grain boundary or in defects or interface, when it is created, then we get the space charge polarizations. Means in the space, in different locations, we will get the polarization due to the applications of the electric field. This is commonly observed in the heterogeneous materials and dominated at very low frequencies. Dielectric constant we'll discuss here, that is called relative permittivity. So dielectric constants is what we are measuring here. We are measuring that a substance, what is the ability of that substance to store the electrical energy in the field, in the presence of electric field. Means that substance will place in the electric field, then we'll understand, or we want to know that quantify that how much it can store the electrical energy. That is called the dielectric constant. So dielectric constant, that is epsilon r, that is the permittivity of the materials in the, and divided by permittivity of the materials in free space. So in free space, relative to the free space, what is the permittivity of the compound? So this is, let's say, permittivity of the compound. Then what we write, epsilon equals to epsilon r into epsilon 0. So this is the dielectric constant of the material. The higher is the dielectric constant, indicates the greater polarization and better energy storage. For any compound, when we are looking for energy storage, how much energy it can store in the presence of the electric field, then it depends on its dielectric constant. Higher is the dielectric constant, higher is the energy storage capability. Physical significance. So here we'll discuss one thing that is called the capacitor or capacitance of a capacitor. In capacitance of a capacitor is called that how much or capability of a capacitor to store the energy. That is the capacitance. So capacity of a capacitor to store the energy, that is called the capacitance. So how the capacitance is made? There will be two electrodes, that is metal conductor, let's say this is stainless steel or copper or something, and another plate we are keeping. Then in between these two plates we are keeping one dielectric substance. Dielectric substance means this is non-conductor, it is not conducting an insulator. We are keeping this one. So this is not conductor, non-conductor, or it is insulator, and this is conductor. This is also conductor. So between two conductor we have one insulator. Now when we will apply the electric field in between these two conductor, then we are calculating this how much charge it can store, this insulator. So this is the capacitance of the capacity. How we will calculate the capacitance value? That we will calculate by using that this capacitance, this what is the area of this whatever taken we have, this on this materials, that let's say this is our device area. Then what is the area of the device? That is called this, let's say this is called a D and this is L. Then area equals to D into L. This is our area, and d is the thickness, or let's say we'll say it's L, because it will again. So this is his area. So this is, let's say, x and y. So area equals to x into y. And now what is the thickness? That is called d. So you can think like this in 3D model. Sorry. Like this. So this is your area. This is your area A, and this is the thickness, that is d. Right, so capacitance equal to epsilon r epsilon 0 a in a by d. So this is the we can calculate the capacitor equivalent. We seen this is used in the in different places, like in fan we used this capacitor. Sometimes it is called the condenser. So what is dielectric loss? So now, just previously we have seen that we are applying the electric field inside in the or in the for a dielectric substance. Now, when we will apply the electric field in the dielectric substance, so it will store the energy, electrical energy. How much it will store? If it is not storing much more, than what other process is going on. So there may be some heat can be generated when we are applying the electric field. The dielectric materials can store the energy, as well as some heat can be generated, or the electric field will be applied, or it will be used for some other purposes. For that other purposes it is used, that we are losing that energy, that is called the dielectric loss. So let's say we are applying electric field some amount, then this electric field is utilized in different way. One is storing the energy, that is main purpose, but some energy is utilized for the internal frictions or charge motions. So these we cannot get back. This is our called the losses we are taking, and losses is taking place. So that is called the electric loss. So that we are not getting back this energy. So how we'll calculate this one? We'll calculate by using tan delta, that is tan delta, that is the ratio of the loss factor divided by the dielectric constant of the materials. Means how much we are losing divided by how much it is stored. So that ratio is called the loss tangent. So from there we can quantify that how much it is storing the charges, or how much it is losing it from this unit. Cause of dielectric loss, for which purpose it is loss is taking places. What is the reason behind of dielectric losses? Lag in dipole orientations. One point is called lack of dipole orientations. Means when inside the compound there will be charge will be oriented after the applications of the electric field, but as soon as possible or instantly this orientation of the charge is takes place or not. If it is taking some time for dipole orientations, but because of it is taking time to orient the charge, so we are not getting the dipole polarizations. So because of this one, this dielectric loss is happening. That process is called lagging, the lag in dipole orientations. So for ionic conductions also, this dielectric losses can take place. Also in the compound there will be defects and impurities, and defects and impurities also can take place in the dielectric loss. Space charge accumulations, this for space charge accumulation also this dielectric loss can be takes place. So these are the causes, the reasons that where how that why the dielectric losses is takes place. Complex permittivity, an alternative to the electric field. Permittivity is expressed in a complex quantity. So what here, if you see, normally we have discussed previously, that is electric field permittivity. What is there, that two things it is happening we are considering. One is how much it is stored the energy and how much it is lost the energy. Previously we made this ratio, that is called how much it is stored, that is called tan and tangent delta, that is how much it is lost divided by how much it is stored the energy, that ratio. Now that we are representing in a complex number, that is this sigma star equals to, this is called how much energy is stored, then minus j or I, this is a complex number. So j, sorry, j and epsilon double prime. So we are representing it in a complex number, that is called complex permittivity of the substance. So this is very important because this is for high frequency and microwave applications, we will get a different properties for these materials. Now, frequency dependent dielectric properties. So what is that meaning? So dielectric properties we are measuring, or we are discussing here, that a non-conductor or insulator compound is placed in the presence of the external electrical field. Now that external electric field, that if we are changing the frequency, then how the dielectric properties of the substance is changed. That is the frequency dependence of dielectric properties. So here what we are doing, we are not changing the materials. What we are doing, we are changing the electric field frequency. So frequency of the electric field is changed. Then we are seeing that what are the properties is, or changes is takes place in the compound. So behavior it is changing. So in low frequency, we will consider in the three terms: lower frequency, intermediate frequency, or high frequency region. Then how it is behaving. So low frequency, space, charge, and orientation polarizations dominate, and high dielectric constant and high losses. So in when we are applying the low frequency, then space charge and orientation polarization is dominated. This process is maximum takes place. The space charge, that is maybe due to the defects, maybe grain boundary, for this purpose, or maybe in interface. So this, the low frequency region, it's changed much more. And high dielectric constant and high losses. For this low frequency, we will get when the high dielectric constant and losses also much more higher. But in intermediate frequencies, for ionic polarizations active. So for let's say for NaCl compounds, these ionic compounds, that movement or shifting, little bit shifting of positive and negative ions in a different directions, then we'll get the polarizations. So these are can be observed in the intermediate frequencies. Then high frequencies. The high frequency to observe in the electronic frequency. That means inside the molecules, that electron will be there surrounded by the nucleus. Then movement of the or shifting or electron cloud. Due to the electron cloud shifting, so there will be a polarizations, because the electron is shifted. It is called the electronic polarization, that can be observed in high frequency region. So this is low electric dielectric constant for this compound we will observe, and minimum dielectric losses. So here electric dielectric constant also less, and losses also will be less. So this behavior of this compound is called dielectric dispersions, where this epsilon r decreases with increasing the frequencies. Temperature dependent dielectric properties. So this temperature strongly affect the dielectric properties, because this ions or the electrons or this dipole moment of the molecules can change due to the temperature. In increasing temperature, increases dipole mobility. So that's why this temperature strongly affect the dielectric behavior. These are the reasons that orientations polarizations increases at fast. So means that orientation which directions that the dipole is oriented, and that one can be changed or modified or change very fast with increasing the temperature. At very high temperature, random thermal motion reduces the polarizations. Means if when temperature is very high, then a particular directions the orientations can change to random way. When it is random way, it will the orientations will happen. Then dipole moment also will be reduced, and dipole moment will be reduced means polarizations will be reduced. Dielectric constant of the polar material shows a peak with temperatures. Dielectric losses generally increases with increasing temperatures. So dielectric constant loss generally increases with temperature, meaning that the energy also we are providing in the means of the electric field due to the increasing temperature, that maybe this energy will be utilized in different purposes. Maybe for thermal reasons, maybe uh, for other purposes as well as. So that's why with increasing temperature, the losses will be more. So that is called dielectric losses generally increases with increasing the temperatures. Dielectric strength. So dielectric strength can be calculated by using this formula that is called breakdown voltage and divided by thickness. Means when we are using a dielectric substance, that dielectric substance, what is the capability of the dielectric substance to withstand this maximum electric field? So how much electric field we can apply for that material? That is called the strength of the materials. That factors which means this affecting this dielectric strength is the material, which material you are going to use it, what is the capability to withstand this electric field of these materials, and what is the which temperature you can withstand, what is the moisture content, thickness of the geometry, frequency, what frequency you are applying the electric field. These are the parameters which depends on the dielectric strength of the materials. Which purposes it is being used? This can be used for capacitor or electrical insulator or microwave or printed circuit board or sensor, actuators or memory device or semiconductor. These are the applications where it can be used. Ferroelectric and high dielectric materials. Ferroelectric materials means that when high dielectric this materials shows that high dielectric constant, but it is also spontaneous polarization takes place in the molecule. So it's called the ferroelectrics. Means spontaneously this molecule inside the molecule polarizations or dipole moment will be created. Then polarizations can be observed. That is called the ferroelectrics. So this compound is barium, titanium oxide, or lead, zirconate, titanate. These are the molecules. So this molecules having a very high dielectric constant. Hysteresis behavior, we discuss this hysteresis later on. Used in memory devices and piezoelectric sensors. So we have discussed here this dielectric what is the dielectric properties, and dielectric what are the materials having the dielectric properties, and what is the parameters which affect the dielectric properties, and which purpose it can be used. So these we have discussed in the sections. So we'll conclude these sessions here.